Thank you. Welcome everyone, and also you new members, welcome. Should we turn down the lights a little bit there, Nick? Turn the lights a little bit down so we can see the screen. Warwick, have we got some handouts for the people just... Oh, thank you. People have just arrived, Warwick's got a handout for you there. That's great. Right, so let's get underway. So this here is the first, or one of the two images released by the Vera Rubin Observatory in June this year, just showcasing some of its abilities to do wide field observations at high resolutions and very deep fields. And what you're looking at here is the Virgo cluster of galaxies, which is our closest and richest cluster of galaxies. It's about 2,000 galaxies in the cluster. But also, what you're looking in the background, there's about 10 billion galaxies in the background. Pardon me, 10 million galaxies in the background. Thank you, Devon. And that is just, that number of galaxies in that image is just unprecedented high resolution quality. Unprecedented. And this here is the second image that they released. And you're looking at here is, we're going to be talking more about these just at the very end of the talk with more depth, but you're looking at the Lagoon and the Trifid Nebula, the star-forming regions, the constellation of Sagittarius, and these pink areas here, these are sort of the nebula there, and that's when new stars are forming. The big massive stars get up running first, they're emitting high energy ultraviolet light, and they illuminate or fluoresce, causing the hydrogen gas to fluoresce. Electron gets bumped off and it comes back on, it emits that pink light. And you're seeing lots of dust and all these gas and dust lines as well. And the purpose of this was just to trial out all their equipment. The proper science doesn't start till later this year, but the purpose of these images was really to demonstrate their ability, what the cameras and the telescope set up, which we'll be talking about, what it can actually do. And that's why tonight's talk is entitled The Vera Rubin Observatory, Charting the Changing Sky. And you'll see why I've chosen that subtitle in a minute. So we're going to have a talk and we're going to have a selection of videos throughout it as well. Okay, so I've split it into two. First of all, we'll talk about the observatory itself and some of its hardware, and then we'll talk about its core scientific missions. So let's talk about the observatory. And we'll talk about the name, why it's called the Vera Rubin telescope, its location, why it's located where it is. We'll talk about the hardware, and then we'll talk about what it's capable of doing. So first of all, the name, Vera C. Rubin. Can people tell me who Vera Rubin was? Yeah, she was a very famous American astronomer who died Christmas Day, 2016, same day as George Michael. It was a very sad day. And she did a lot of work that was able to, some good evidence, strong evidence of there being what we call dark matter, whereby she observed a number of spiral galaxies, and she's able to plot what we've got here. Let's just bring this into line. There we go. And this is one of the galaxies she observed. This is called the Triangulum galaxy. It's one of 3 spiral galaxies in the local group. And she was able to plot the velocity or speed, if you will, at which stars rotate around the centre of the galaxy as a function of how far they are out from its centre. You can see this superimposed graph here. There's the velocity in kilometres per second, and this is in light years going out here, 10,000, 20,000, 30,000, 40,000 light years going out from the centre of the galaxy. And what normally you'd expect for the laws of physics, Newtonian physics, you'd expect the velocity of them to go up and up and up, and then the velocity for them to tail off like that. But what she observed in these spiral galaxies is the velocity just kept getting faster and faster and faster and faster. And with the laws of physics, that tells you just one thing. There is some unseen material further out here that's having a gravitational influence on the galaxy. And that was very, very strong for dark matter, which we'll talk about later on. So that was very groundbreaking, and the telescope and the observatory is named after Vera Rubin. So where it's located on a mountain top in northern Chile, at the end of the Atacama Desert. Why is it up there? It's at nice high altitudes where it's above most of the water vapor. The climate up there in the Atacama Desert is very dry. It's one of the driest places on Earth. And where you get these sort of areas, these dry areas at high altitudes, you've got less distortion of the atmosphere, you've got less water vapor and so on, so you're getting much sharper, clearer images. Of course, because it's so far away from cities, less light pollution, and of course a lot of the major telescopes are in the northern hemisphere. The southern hemisphere actually gets a better view of the Milky Way, so a lot of the big telescopes are based down here in the southern hemisphere, so it gets to see a large part of the sky that the northern hemisphere telescopes don't see. So it's a very prime, there's a lot of telescopes, big telescopes right along here through the Atacama Desert in Chile for that exact reason. It's nice and dry and it's high altitude. So here's a cutaway picture of the observatory, and you can see the telescope with its optics and its camera up here in the top level, which we're going to look at more closely shortly. And then down here in the lower level, you've got tanks with very specialised coolants for the operation of it. Now that's what the telescope looks like with its mounting. It's a nice close-up diagram, and so we'll look closer at that now. So that's the configuration. It's a very unique three-mirror design, an aerostigmatic design, and it's the reason they've chosen this, and I'm going to go over the light rays very shortly to show you, but it's this type of optical setup, because you might say, well, why don't they just have a normal telescope setup with two mirrors? Two mirrors opens itself up to a lot of what we call aberrations, optical aberrations or distortions, particularly around the peripheral views. And if you're going to do wide angle observations, you want to minimize that to the maximum. So this particular design minimizes the distortions in the wide field. So you can see the light rays here. So light's coming down here, hits the primary mirror, goes up, hits the secondary mirror. The light then gets directed down to the tertiary mirror, and that's what makes it special, this tertiary mirror. And then the light from there goes up, directly up into its camera system up in there. Now, to make that a little bit clearer, I've got a nice little video here. There you go. So there's the light going down to the primary mirror, going up. There it goes up into the secondary mirror, down to the tertiary mirror, then right up to the camera. I've just done that. When I've given this talk before, people often like to look at it a second time just to take it in. So I've just done it again, just a little bit quicker. There's the light beams going down, primary mirror, up to the secondary mirror, down to the tertiary mirror, and then reflected back up to the camera. So that's its set up there. So why has they've done all this too? And there's a few points here. One is that three-mirror setup, to minimise distortion in the outer fields, particularly important with wide angle. Its primary mirror you saw there is nice and large at 8.4 metres. That's a decent sized mirror. And of course, the bigger the mirror you've got, the brighter images are, so you can see smaller, fainter and more distant objects because the larger mirror collects more photons of light. So that's unprecedented before in this typical design. Those technically minded out there, with their optics, it's very what we call a very fast system with a very low focal ratio of 1.234, which means that it's ideal for taking wide field views, which is great for surveying, but also it means it can get a very quick, bright image with a very short exposure time. So it can quickly take a quick snapshot with a few seconds, get as much light in as possible in that time over a wide field and be able to move on again. So that is one of the biggest advantages of having this whole setup with such a short focal ratio. So as I mentioned, 8.4 metres for the primary mirror. And you'll notice here that it's all in one configuration. They've put the tertiary mirror in the middle of the primary mirror there, and that's 5 metres across there. And the second mirror up in here, that's 3.4 metres across. That's the largest operational convex mirror that they have, that's been built so far. Then up in here, you'll see they've got the camera, the largest digital camera ever built, 3,200 megapixel cameras. That's huge, what, 3.2 gigapixel camera. Largest digital camera ever built, and that's incorporated into here. So you can see where the light from the primary mirror goes directly up into that. Here's a nice close-up picture. This is just be pre-installed. There it is there. So the largest camera ever built. I've got a nice picture of that here, or a diagram of that here, to put that in perspective. There it is there. You can see a technician up against the lens of it there. It's the size of an SUV, and it has 3 corrector lenses in the front here as well. And the idea behind them is, even though you've got this 3-mirror design to minimize your distortions out to the outer parts of these wide fields, you're still going to get some, and they want a perfect images, the best they can. So they've got 3 corrector lenses right up front as well to try and correct those. So they've gone all out to create very short, quick exposures to get bright images over very wide fields with minimal distortion and the best resolution they can with that nice big 8.4 metre mirror. So you can see it's a very unique and particular setup that they've got going here.
Chris, the primary and tertiary mirror, are they single cast or segmented?
I think they're seconded, I'm pretty certain, yeah. Yep. Okay. So here we go here. Now, then on top of that, we'll put the circle up there. There's 6 specialised optical filters in there as well, which we'll have a look. This is on top of all your lenses stuff. You've got 6 filters in there. They're called broad spectrum filters. And the range here is from in the 320 nanometers, which is in the infrared range here. So you've got this one here in blue. That's your infrared, your ultraviolet here. You've got your visible wavelengths here to about 700 nanometers, and there's your infrared here. So they've got 6 these broad spectral band filters here, which we're going to talk a lot more about those later on. But I think I have got a little bit more about them here. So why do they need all these filters and cover? This is another special feature of the whole setup. It covers such a wide range of wavelengths. Can do ultraviolet, which is in the UV band there, which is in the blue to the left-hand side. That enables them to look at the sky in ultraviolet, where a lot of energetic events are happening, big bright stars blazing out in ultraviolet energy, and also high energy events such as gamma ray bursts and the like as well that go into the ultraviolet. Then you've got 3 bands, the I, Z and the Y over the far side on the right here. They look into the near infrared part of the spectrum, and the importance of their infrared astronomy is very important. You can cut through dust. So if you get dust enshrouded, like new stars forming that are totally enshrouded in dust, that block visible wavelengths of light, ultraviolet just goes straight, your infrared just goes straight through that. So they're able to see those as well. So the bottom line is it covers a diverse range of astronomy across multiple wavelengths. So that in itself is amazing. Yeah.
Do you know, can that do it all at the same time, or do you have to...
They change the filters over, which we're going to talk more depth about the filters shortly. Yeah. So, looking now at the optics, and the camera actually mount itself is just incredible. So it's a very rigid but a light structure, and it's floating on the surface of high pressure oil, which allows it to be very mobile and adaptive, which I've got a nice video showing that shortly. But that allows, they want minimal vibration, and because they're going to be surveying the sky, they want it to be able to move very, very quickly and very, very precisely, bang on, with little resistance. So it's essentially floating on a layer of high pressure hydraulic oil. So it can change its position. Look at the sky, focus on a certain part of the sky and quickly skew across, 5 seconds flat, bang. It's focused, beautiful, nice and steady and stable on another part of the sky. So we're getting into its capabilities now. Yeah, so as I mentioned, So when it looks at a certain part of the sky, it just takes 2 15-second exposures, and it only needs 15 seconds because of that optical design, that short focal length, whereby it's able to just instantly get a quick snapshot, and in that 15 seconds it picks up a lot of images. So it takes 2 15-second exposures, and then within 5 seconds it slews over to another part of the sky, focus, gets ready, takes the next 2 15-second exposures. Total field of view, first exposure, 3.5 degrees in diameter, which equates to about 9.6 square degrees of sky, which is about 45 times the size of the full moon. Probably saw the full moon tonight out there. Yeah, so imagine 45 times that, and that's one single exposure, that part of the sky. Bang, 2 15-second exposures, 5 seconds, moved on to the next side. So straight onto it. It scans the complete southern sky every 3 days. 1,000 images per night. It's able to plough through, and each time it's that second exposure for each time it's sitting in the sky, it gathers more light, and of course 3 days time it's back on that same spot again, it gathers more light again, and they stack that up, and they just keep getting more and more exposures over time, and they're able to pick up and get deeper and deeper into the sky, and brighter images of faint objects. Over 10 years, its mission over 10 years, it hopes to complete 825 complete scans of the sky over 10 years. And its purpose is what they call the Legacy Survey of Space and Time, or the LSST. And it hopes to look at, there's my billion, a billion galaxies. There's 10 billion galaxies that it hopes to observe over that time, over those 10 years, 825. So in other words, you multiply that by 2, and there's the number of exposures of any object in the sky over that time. So here's a nice little video I've got here. We'll just get the sound sorted out. This guy here, Chris Nichols, does a very good summary and has a look around the telescope. So here we go.
All right, so this is a really cool opportunity. We actually get to see the Simony telescope, the LSST array. It's all moving, and I mean, what you're seeing right now is it moving slowly. It moves much faster than this. And remember, we talked about the fact that this can shoot the entire southern sky in 3 nights. I mean, that is incredible. No other telescope can do that, and it's thanks to this powerful design and very interesting motors. And this is so significant because, look, there are other telescopes in the world that have similar fields of view, but nothing that can shoot at the relatively fast shutter speeds that it does, at the speed that it's able to traverse the sky, and how many photos it can take over time. I mean, that means that the dome moves quickly, the scope moves quickly, and all of this while everything's in focus and aligned perfectly. And so how do you move the world's largest camera in this giant telescopic array smoothly and quickly? Well, it's actually fluid dynamics. So they're actually pumping high pressure oil from below, and the array is floating on this oil. Now, I've been told it's not baby seal oil, it's not 5W40. I've been told it's synthetic and that's it, but it's pumped at extremely high pressure, to the point where the array is actually so easy to turn that we've been told the petapixel team could actually by hand rotate this entire array. They are not going to let us do that, but 3 people can actually move this thing by hand. But the speed goes beyond just the actual physical movements of this telescope or how fast the camera can fire. It also comes down to how quickly they can transmit data. We're going to talk about that next. Okay, so I've been told that it's quite noisy here, and that's because we've got the data processing center right behind us here in this room. Now, all those images that come out of the camera, they're actually immediately sent from the back of that room directly to the SLAC laboratories in Stanford, where we first saw the LSST in our first video. Now, this is incredible because they have a fiber optic cable network going from here all the way to SLAC directly 103,000 kilometers. Now, these images, I said, are about 25 gigs. They're compressed down to, let's say, roughly 8 or 9 gigs and sent over the fiber optic network, and they arrive at the SLAC laboratories in less than 10 seconds. And this constant streaming of data is very important because they can only store the information here at most for like a month's worth, and then it's full. But the SLAC laboratories, way more storage to start to contain all this. Now, this information does actually have to be held for about 80 hours, and I know that has some consternation amongst the scientific community, but we've been waiting for a lot of this data for billions of years to come here. What is another 80 hours, right? I do want to mention, though, that alerts will be sent immediately. Within a matter of minutes, that'll be sent out to the scientific community. And alerts can be anything like the brightness of this area changed dramatically, or an object that was here is no longer here, or this has moved a significant amount. We're talking about, I don't know, something like 10 million alerts every night. So there's still going to be tons of data released immediately. So the actual data throughput is fascinating. It takes these very loud computers to operate, but I can even say, I mentioned scientists love photographs, and yes, James Webb, Hubble, they capture beautiful color imagery that just sparks the imagination of the public. But the Rubin Observatory can also make beautiful photographs. And what we're here to be a part of is to get to experience these first public images released, so let's take a look at them now.
The engineering behind it, the science behind it, just an absolutely incredible. We're talking about that 10 million alerts per night and that amount of data. So that's the observatory. So let's move on now to its core scientific missions, what its sort of prime purpose of doing. As I mentioned before, it's the 10 year, it's going to be operating over 10 years for its primary mission called the Legacy Survey of Space and Time. And the bottom line, as we talked about earlier on, it's ultra-wide views, ultra-high definition, and because it's constantly scanning the sky, it can compare images with previous days, previous years, over the next 10 years, where it's going to be looking deeper and deeper as it does that. So they're going to, of course, in space, because the speed of light is finite, the further you look back, the further you're looking back in time. So they're going to create a time movie, if you will, of the universe at high resolution, wide angle. Never been done before. And it's just mind-blowing. So it's 4 science missions, these ones. We're going to be talking about each of these: probing dark matter and dark energy, exploring the transient optical sky, cataloguing the solar system, and mapping the Milky Way. So let's talk about each of these now. So first of all, what is dark matter? And I touched upon that briefly before talking about Vera Rubin, who provided some strong evidence for dark matter. So dark matter is a hypothetical particle to explain observations whereby there's evidence for material out there that we can't see, which means it doesn't emit light, it doesn't absorb light, or it doesn't reflect light. It doesn't interact with light. So we can't see it, but it interacts through gravity. So we can see it's there because of its effect it's having on other matter. And a good analogy to that, for example, is wind. You can't see wind, can you? But you're sitting inside a windy day, you can see that the trees are leaning over, you might see a rubbish bin rolling down the street, so you can see the effects of the wind. You know it's there, but you can't see it. That's the idea behind dark matter. There's some sort of hypothetical matter out there. It makes up actually 85% of all matter. So out of all the stuff, the matter, not counting energy, that's another part of the equation again, but just matter, 15% is this normal stuff like us in this room, 85% of it we cannot see because it doesn't interact with light.
Sorry if I may, Chris.
Yeah.
How do we know it's matter and something that we don't understand?
There is all these theories about that. I got a nice talk on dark matter where I argue it's some sort of particle, almost certainly some sort of particle. There are people saying there could be some other laws of physics and stuff going on to explain it, and they loved putting that into the context of spiral galaxies, those rotation curves. But there's a whole stack more evidence on larger scales that really points to it being a particle, yeah, which fits in nicely. So I've got a talk on that too.
So it has mass.
Yes, it's mass, it's matter, yep. Now, so how do you map out stuff that you can't see? It all comes down to what we call gravitational lensing, which is part of Einstein's theory of general relativity that he developed and released in 1915, and whereby he showed that all matter, whether it be normal matter, including dark matter, it warps space-time around it to create a lens effect, what we call gravitational lensing, whereby if you get an object, say if we're here, you get an object here that's emitting light, and between your line of sight, if there's a cluster of galaxies sitting here, the massive amount of mass in this cluster of galaxies simply warps space-time and creates a lens effect where light goes around it, comes back again. And that gives a brightened, magnified, distorted, arch-like images of objects behind you. And that's called gravitational lensing. So that's how they're able to do it, by the influence that dark matter has. And there's two different types of gravitational lensing. There's what we call strong lensing, and that's where pretty much what I've just described here, whereby the light from more distant objects, way back here, behind us as it comes towards us, sitting around here, there's a galaxy cluster. So the light from behind gets arch-like and distorted. And this is called an Einstein ring. There's Einstein rings, Einstein crosses and various things. Or sometimes you just see simple arches going around as images of light from way cosmological distances, way in the distant faint galaxies. The light gets magnified and distorted. And the idea from here is they analyze the distortion, and from there they're able to calculate how much matter must have been in the foreground to distort the light in the background. And of course they see how much matter is there in normal, what we call baryonic or normal matter. So you just 85% of the total matter is dark matter. So that's and that's once again all those other different laws of physics stuff does not explain that. That's a huge thing to say, that it actually is some sort of matter going on with its gravitational influence. So that's strong gravitational lensing, so they'll be doing that. And there's also another one called weak gravitational lensing, and that is whereby just statistically millions and billions of galaxies in the background, their shapes are just very subtle distortions on a statistical basis. And they're able to measure that and calculate that out, and from there deduce how much dark matter is between them and all these other multiple galaxies. So they're able to get an idea of the amount and the distribution of dark matter in the universe. And that's pretty important. To understand the universe, we've got to understand dark matter. They haven't yet found the particle. There are some gaps in the standard model of particles, that some of the particles such as axions would fit in quite nicely with that. They're searching for those particles, but that's where the evidence seems to be pointing. So that's interesting. So it makes sense you've got to map out where your dark matter is to understand it more. So it will be doing that over the next 10 years. Dark energy it's going to be probing. So what is dark energy? Dark energy is it's an unknown force that appears to be causing the acceleration of the universe, or the expansion of the universe. So the expansion rate of the universe is not constant. It appears to be increasing at the moment. There's some speculation that may change again, but what is driving that? They call it this thing called dark energy. And so 3 ways to probe dark energy. Well, if you can't see the energy, we don't understand what it is, but you observe the effects that it's having on the universe to help you try and understand the dark energy itself and process the universe. So there's 3 ways to probe dark energy, which each of these we're going to go over: baryonic acoustic oscillations, type 1a supernova, and galaxy redshifts. And the idea really is that dark energy is pushing galaxies and clusters of galaxies away into the distance. We've got a whole talk on that we do from time to time. So if you can study and document how galaxies have been moving apart from one another over the last 13.8 billion years, that gives you a deep understanding of what's going on. So what are baryonic acoustic oscillations? And the bottom line is, they're imprints of circular concentrations of matter from the early universe. When the universe was in the first 380,000 years, it was all opaque, And it was just a massive sea of charged particles, and photons of light weren't yet free to travel. It was just totally opaque. But for reasons which we go into another talk, beyond this talk, there were sound waves that got set up, compression sound waves that were going like that throughout the whole thing. And that created these circular distributions of matter as it was going in and out, the pressure of radiation going in and out. And then after 380,000 years, the universe became opaque. That's another whole story, and light was free to travel, but you still had these circular arrangements of matter that turned into galaxies. And of course, as the universe expanded, these circular arrangements, statistical now, circular arrangements of galaxies, just keeps expanding. And let's just expand this one up here. And you can see this gives you an idea here that galaxies statistically are arranged in these circles here. And that's what they do find to this day when they map out the universe. And they are imprints left over from the sound compression waves from the very early universe. So with time, they've been expanding. So if you can measure them over time, determine the age at which how far you're looking back and how big those statistical circular arrangements of galaxies are, that tells you a lot about dark energy, how and where it's operating most. The other way is through type 1a supernova. So supernova, you're probably aware of that, and that's when a star explodes and goes supernova, and you get a massive bright light at the time with the supernova explosion. There are different types of supernova beyond the scope of this talk, but there's a particular type called 1a supernova, and that's where you get a remnant of a small star called a white dwarf. It's really, really hot, blazing in ultraviolet. And if it happens to be in a binary system, a close binary system with a red giant, that white dwarf, because of its gravity, siphons the material from the red giant or red supergiant onto its surface. And when that material reaches a critical temperature, you get boof, you get nuclear fusion, thermonuclear reaction, it ignites up, and the whole star, the whole white dwarf just explodes in one massive explosion. And that's called a type 1a supernova. And the importance of that is by far, out of all the different types of supernova, that is head and shoulders the most brightest. But more importantly, because all those things happen at a certain threshold, when the white dwarf gets to a mass of 1.4 solar masses, times 1.4 times the mass of our sun, exactly that moment, that's when you reach the threshold which the explosion occurs. So they understand the physics, and they can quantify the physics that's going on, so they know exactly how bright, the absolute brightness of a 1A supernova, they know exactly how bright it should be because the physics is well understood. So if you observe one of these supernova and you measure its brightness and you know exactly how bright it actually is out there, it's a very simple equation to tell you the distance between you and that 1A supernova. So it follows from there that if you're able to observe many of these 1A supernova as you possibly can, and you know the time at which of the how far back in time you're looking, you can work out from there the expansion rate of the universe at that moment in time that you're looking back through the history of it. So that's another beautiful way of finding out the expansion rate of the universe at different time frames. And remember, it's going to be doing this with unprecedented precision, resolution and precision that hasn't been done before. Because you might say, have they done all these studies with these other telescopes? Not to this degree of precision. This is really something really special. Then there's the thing called red shifting to make out 3D maps. And they use a process, and this is where you think about the nice broad spectral filters comes into play. So let's talk about measuring distances with redshifts. What do we mean by that? What are redshifts? How are they measured? And what do they tell us? And part of these talks too is this introduction to astronomy. So I take advantage that we're talking about the Vera Rubin Observatory, but it's a great vehicle to talk about principles of astronomy. So that's what I'm trying to do here. So what are redshifts? And the point here is that, as sort of we briefly mentioned earlier on, that light comes in a wide range. Light is continuous waves of alternating electrical with magnetic energy fields, and it's just alternating like that. So they form a wave pattern, and they come in wavelengths. And in the middle there, you've got a relatively narrow strip that's expanded out here called visible light, red through to blue. And it's that part of the spectrum, that very narrow part of the spectrum that our eyes have adapted a sensitive and that we can perceive with our eyes, being from blue through to red. But of course, there's much more to it than that. As wavelengths get shorter, energy levels go up, and you get your ultraviolet, then your X-rays, and then your gamma rays. Go in the opposite direction, wavelengths get longer and longer. You're going to weaker photons, infrared, you've got microwaves, and then you've got radio waves there. So that's a little bit about the electromagnetic spectrum, how light comes in a wide range of wavelengths. Now, so if you get an object like a galaxy full of stars and so on, and in the early universe, and they start emitting light, let's just say high energy, a big bright star, early universe, starts emitting light and ultraviolet wavelengths, short wavelengths. But it's for the last 13 odd billion years, while that light wave has been travelling towards us today, the universe at which that light is embedded in is being busy expanding. So what happens, those wavelengths of light are getting stretched longer and longer and longer. And you can see here from that last diagram, you can imagine that they would be stretched out from the ultraviolet into the visible wavelengths, and then eventually into infrared and so on. So if you can measure how much those wavelengths of light have been stretched out over time, you can measure how far away or how far away in time that particular object is. And that's called red shifting. So the longer the wavelength, the older the light. And there it is there, it's been shifted across. So we say that light has been red shifted. And there are two methods to measure redshift. And we've talked about it in the past, but I'll just review very, very briefly. There's spectroscopy. But there's another method called photometric, which we'll be talking about. So the first one is the spectroscopy. And the idea there is that you get an instrument called a spectroscope, you put on your telescope, and it splits like a prism or some grating that we've talked about previously. But as you imagine a prism, you'll see one of the idea behind a prism, how it splits white light into all its various colours, that spreads it out through there. And so you put that on your optical telescope and it spreads it out. But in the atmosphere of stars that you're looking at, there are elements, and those elements absorb the light coming out of the star and cause what we call absorption lines, where it absorb the light. And those little absorption lines there are very, very specific, like fingerprints, if you will, for certain elements and certain energy states. So the astronomer will look at it and they look at the light, they look at the lines and they'll say that's a certain element at a certain energy level. They get to know that, and they get to know exactly where those lines would normally fit if something was directly in front of us. But if you got something that's far away and you're getting it red shifted, these absorption lines all get shifted to the red, as you can see here. And that's called red shifting. And you can see it here. So this is, say, a spectrum with the spectral lines here in the laboratory, say on Earth, and that's where the lines would normally fit. And you can see here's a nearby galaxy. The lines just slightly shifted, but they're pretty close to lined up where you'd expect them to be. You go out to a more distant galaxy here, see the lines have been shifted further, and you go to a very distant galaxy, and these lines here have been all shifted over to the left-hand side. Why? Because the wavelengths of light have all been stretched out as that's been travelling through the universe. And that principle is called redshifting, and that's how they measure the amount of redshifting through a spectroscope or spectroscopic measurements. And there's just an explanation of it there. You can see as a galaxy is getting further away from us, the wavelengths are getting stretched out. And you see this absorption line here, that's getting shifted more and more over to the red. And there's very simple formulas that the astronomers have got to, the degree of redshift, the amount of change of wavelength divided by the actual wavelength of it. Very simple formula. You can work out how much redshift has happened, and from there, just carry on with the formula and you work out how far away that galaxy is in time. So that's the spectroscopic method. Now, that is really high precision, but it's not ideal for surveys. That's the sort of stuff that you'll see with your James Webb, and that narrows down, very focused, and can sit and look at an object for as long as they want to, is practical, and get very accurate assessments. But it's not ideal for surveys. And that's where your second method comes in. And this is where the Vera Rubin Observatory comes in, the photometric method. And what it involves is looking at an object through your different filters, like here, and there's one here, there's an object here through different filters, and you keep looking at the object, and eventually it drops off. And the whole idea behind this is that you get a galaxy yay far away from us, and in that galaxy you've got these stars of various sizes and energy levels emitting light right across the spectrum. You know, your infrared, your optical, and your ultraviolet. And neutral hydrogen gas within the galaxy and all the intergalactic gas between our line of sight between us and that particular galaxy, any neutral hydrogen gas absorbs ultraviolet light. Anything greater than about 912 angstroms, which is 91.2 nanometers, it's just depending which unit you want to use. You're getting into ultraviolet, they tend to use the angstroms. But your neutral hydrogen in that galaxy and an intergalactic gas between us and that galaxy, the hydrogen absorbs any light of a wavelength shorter than, in other words, higher energy photons, any wavelength shorter than 912 angstroms. So from there, it shows that the brightness of a galaxy, wavelengths bigger than that, in other words, less energetic photons, will shine through, and we'll see them through our filters of those right up till then. But anything above 912 angstroms, that's going to drop off, isn't it? So that's called a Lyman break. Is what that line is, where the light gets cut off, where you no longer see it through here. But once again, all that light has been travelling towards us, and the further an object away, that Lyman break, where it suddenly drops off, moves from the ultraviolet, far ultraviolet, to the near ultraviolet, into the visible wavelengths, and eventually into infrared, where it starts to drop off. So that's called a Lyman break, and you drop off. So let's have a look at a little bit more about that here. So here you've got 5 filter bands going on here, and these little crosses here, that's the levels they've detected in the band. So here's your band, there's a level here, they've got a level here, they've got a level here, they've got a level here, and notice, whoa, this band, it's hardly, there's hardly any visibility at all, brightness. And what they do is they use models, computer models, to do a best fit, lines like that to best fit to meet these data. And they can say, well, there's your Lyman drop off there, for your Lyman break. Now here is one here that they've used. So you can see this is they've encircled a galaxy here. See it in the I filter, nice and bright. The V filter, nice and bright. The B filter, you can still see it. It's getting a bit blurry, but you can still see it in the near ultraviolet. But you go into the far ultraviolet, which is this bit here, bang, you can't see it anymore. It's dropped away from your filter. So that's the Lyman break is lying in here. You work out exactly at where you put your model. You make your curves and stuff through your models here, your computer models, your best fit, and you work out where the drop is occurring. And that tells you, once again, simple formula, you know it should drop off at 912 angstroms, but it's not. It's dropping off at longer wavelengths. And the simple formula to work out that tells you the redshift of that galaxy, which tells you how far away and how old that galaxy is, and how old it was when you're looking at it. This is a redshift of z equal 1. They use a thing called z equals 1 here to describe distances. So that's called the Lyman break, and that's called the photometric method, and that's another way to work out redshifts. And it's less precise than the spectroscopic absorption lines, but it enables rapid estimation for large numbers of faint, distant galaxies. And that's the whole point of this telescope. It's when I say it's less precise, it's still damn precise, still very, very good, because you've got these computer models doing your best fits. Make no mistake, it's not just a rough estimate. No, it's a very, very good estimate. But it doesn't have to be precise, and it's just good when you're doing these wide field scans of the night sky. You're looking at multiple, you saw the multiple millions of galaxies per shot that it's able to get. It's able to analyze multiple galaxies very, very quickly and get a very good estimation of the distance of those galaxies. In other words, how far back in time are you looking? So this is the method that it uses to measure redshifts, which, going back to our original thing we started talking about, this is one of the 3 methods they use to probe dark energy. Okay, so if you can map out all these millions and billions of galaxies, the exact position in the sky and how far away they are, and how they're moving with time, because we're doing a 10-year time lapse, you can start creating these sort of movies, these computer simulations. And there is the Sloan Digital Sky Survey data simulation that's done this to a larger degree, but nowhere near to the precision and the resolution that we're going to be getting from the Vera Rubin telescope for the next 10 years. But I just wanted to just play a few seconds of this just to give you an idea of what they can do with. So this is real data that they've put into a computer simulation. But once again, you can see the statistical arrangement. There's a big cluster of galaxies here. We're in a big space here. But you can see here the cosmic structure. It's not just random. There's structures that it's going through, clusters of galaxies. There's statistical circular arrangements of galaxies in there. You can see in there. So that's a three-dimensional image. So when you go home tonight, someone says, what were you doing? You can say, oh, I saw a simulation of the entire universe. Why, what did you do tonight? So that's what you're seeing there. I'm going to show you an image later on. So the Sloan Digital Sky Survey was done with 2.6 metre telescopes. Remember, we've got 8.4 metre telescopes here. Remember, the bigger the telescope, the more brighter and the better resolution you can get and see fainter objects. And I'm going to compare an image from this with the images of the Vera Rubin. I'll do that at the end. So that just gives you a taste of what they're planning to do. So that's probing dark matter and energy. It's also going to be exploring the transient optical sky. What does that mean? Things that changes, essentially. So it's going to be trying to pick up anything that moves or changes in brightness of the sky. It's going to be picking up. Why? Because remember, it's doing all these exposures every 3 days. It's moving to exactly the same spot in the sky. If something has got fainter, if something's got brighter, or if something's moved in position, it will pick it up and alert the astronomers to have a closer look at it. As the guy said, they expect 10 million alerts per night. Think of the data. They're obviously going to need some AI to sift through that there. So what is that going to be used for? Explosions, like supernova explosions, and other things like kilonovas, the afterglows after gamma ray bursts and so on. Variable stars are stars that pulsate at certain rates. So it'll be able to pick up previously undetected variable stars. And of course, more locally, asteroids and comets as they move across the sky. It's going to be very good at picking those up as well. So anything that changes in brightness or moves, it will pick up. Cataloguing the solar system. You might think, oh, we know what the solar system is all about by now.
The biggest worry they've got from that is this, and I've seen through like 50 mil there tonight, is that we've able to filter that. There's no other resources to process that much data. They have to filter which choose which ones they look at. They're also scared they're going to miss major discoveries because they filter them out.
Yeah. The amount of data is just going to be, the logistics of it, incredible. Yeah, absolutely. So the idea behind this with the solar system is to identify and track previously unknown asteroids, comets, Kuiper belt objects, and are there any possibly distant planets out there? Everyone talks about Planet X and so on. Is it out there or not? This will give us an idea of what's way up in the solar system beyond our reach at the moment. So that in turn will help them understand the solar system better, what's there and how the solar system formed and evolved and so on. So in the first 10 hours of operation, when they did this trial run for these publicity shots, it detected over 2,100 previously undetected asteroids. And that sort of exemplifies what Andrew was saying. There's just so much data there. And
It's 1 night.
yeah, that's one night. Yeah, one night, first 10 hours, 2,104 asteroids. You're going to be talking, these are invisible wavelengths. So your answer to your question is you put one filter on at a time.
No, I mean, like when you search something, like on Google or something, you filter it out. So like you could do something to a certain size or a certain type of thing that happened.
Then you started
Filtering the data.
Right, that's filtering the data, not filtering on the telescope, it's filtering the data.
But you wouldn't miss things if you
Yeah.
could find what you're looking
And that's what Andrew's alluding to too. Yeah, it's going to be a whole logistics issue in itself. Yeah, yep, absolutely. So they expect to discover up to 100 times more objects that we currently know in the solar system. And of course, the importance of this, and too, that's what Andrew was alluding to, There's going to be so much bits of data stuff here. We don't want to be missing something really important we should know about, like an asteroid or such, or a comet that's heading towards us. So, but the point being is our understanding depth of knowledge about the solar system is just going to explode with this Vera Rubin observations. And then other things is mapping out the Milky Way to understand the Milky Way better. And the Milky Way didn't just come about in itself in its own structure. It had to form initially, it was a lot smaller and slowly formed and engulfed a lot of smaller satellite galaxies that come nearby and engulfed it all and so on. And it's made up of stars of different sizes and temperatures and energy levels, but also what we call brown dwarfs, which are failed stars, which haven't got sustained nuclear fusion. They're very elusive and hard to detect. It's going to be able to pick up them. And as I alluded to here, this is what we call stellar streams. So the Milky Way just didn't come about like this very crude diagram here of the Milky Way. But along the way, it grew by cannibalizing, munching on and pulling in smaller galaxies around it and orbit around it, small dwarf galaxies, irregular galaxies and so on. And the galaxies don't just suddenly flock into the Milky Way. They sort of go around the Milky Way a few times and they leave trails, what we call stellar trails of stars behind them as they get slowly swallowed in. And they are aware of these, what they call stellar streams, where a galaxy's been slowly going around and orbiting the Milky Way and slowly getting ripped apart and absorbed. So if you can identify these stellar streams, see where they are, how big they are, what are the type of stars that are in them, that's going to give you a lot of information to look at how the Milky Way originally formed and how it's evolved over the last few billions of years. This is just stuff they have not been able to do. The Vera Rubin will be able to do this. Variable stars, we briefly mentioned before, these are stars that pulsate at certain rates, and a lot of them called Cepheid variables, which are big supergiants. They've been known, the rate at which they pulsate at is directly related to how bright they are. So if you see one of these stars, identify one of these variable stars, you look at its rate of pulsation, therefore you can work out how actually bright it is, absolute brightness. You measure how bright it looks from Earth, so once again, simple formula to work out its distance. So there's a lot of variable stars right on the outskirts of the Milky Way that we just haven't been able to see yet because we haven't had the resolution to be able to pick up these objects. So if you can identify the most distant variable stars in the Milky Way, you'll be able to map out the actual distances. Where is the most outer reaches of the stars in the Milky Way galaxy? And that is what this is going to be able to do. And furthermore, if looking at all these stellar streams and stuff, the Milky Way itself is embedded in a big halo of dark matter, whereby they estimate about 90% of the matter that goes to make up the Milky Way galaxy is actually all dark matter. The matter that we actually see, stars and so on, is only about 10% of the matter of the Milky Way. There's another 90% of it in a big massive halo. So studying these stellar trails, if you will, and streams is going to give a lot of information to be able to work out the distribution of dark matter around the Milky Way as well. So just wrapping up the summary before we look at a video and some images. So summing up the observatory, that primary mirror is large, 8.4 meters. That enables it to see small, faint and distant objects. The optical system, that 3-mirror system, is with a short focal length, is ideal taking for wide angle and for bright, fast images, which is just short images, short exposures rather, that give you nice bright images, and it's ideal for surveying, very efficiently surveying the night sky in high resolution. And of course, its camera, the largest digital camera ever built. And the science, as we've gone over, it's probing dark matter and dark energy, looking how things change during the night sky in positional brightness, cataloguing the solar system and mapping out and learning more about the Milky Way, of how it formed, how it evolved and its current structure. Now, just these are these first images. That, by the way, is the Sloan Digital Sky Survey. There's 2 of them as twins. That's got a diameter of 2.6 meters. And here's the Virgo duster that data. So here's the Virgo cluster from the Sloan Digital Sky Survey. This data was used to form that computer simulation, how we went through space. So that's a picture of the Virgo cluster. Now let's just review what it looked like through the Vera Rubin. Amazing, isn't it? I'll just go back a minute. There you go. That's the difference between the two. So this is going to be, in this resolution, going to be surveying the night sky over 10 years. Just mind-blowing. This is the one here. This is Fraser Kane from Universe Today. I highly recommend the site. It's great on YouTube. And this is just about a minute to a minute and a half long. And he just goes over these two images and talks about some of the details of stacking the images and so on. So I'll just run this through.
So with the images, we saw this incredible image of the Trifid Nebula, Lagoon Nebula complex. And these are two star-forming regions that are very close to each other. They're really famous. They're located near the center of the galaxy. I've taken pictures of them with a small telescope, but nothing like this. And so this picture was made of 678 separate exposures that were then taken for about 30 seconds and then stacked up together to create this just incredibly detailed image of the complex. And then the other image that they released was of the Virgo cluster. And this is the sort of largest cluster of galaxies close to the Milky Way. And they kept showing how you don't own a screen big enough to be able to see all of the detail in this picture. And that's because it was taken with Vera Rubin's 3.2 gigapixel camera. You would need many, many screens bolted together to be able to see the full image at the full resolution. But they were able to provide a viewer on their website. So you can go and zoom in to different parts and zoom back out and move to a different spot and zoom in to really get a sense of the level of detail that are in these images. And again, this was made with hundreds of separate exposures and then stacked up. But this is a demonstration of the field.
Yeah, there you go. Pretty amazing, isn't it? Incredible technology, incredible data and stuff they're going to be getting. And that, my friends, is the Vera C. Rubin Observatory charting the changing sky. Thank you very much. Are there any questions out there? I may not be able to answer all the technical questions, but I'll have a, yeah.
Yes, I've never heard of it until tonight, but it's been, the observatory's obviously been in the planning for many, many years. So who are they? You mentioned they. Who's behind it? Who built it? Who runs it?
Yeah, now, originally it actually started off, it involves numerous consortiums and universities. I can't tell you who does it now. I know one of the guys, one of the famous guys, a technician guy behind who Excel spreadsheet, he was one of the first guys who actually put money and got it going. And I couldn't tell you, that's worth looking up. I couldn't tell you. Does anyone here know?
Simonides is the name of the telescope. So the telescope itself is called the Simonides survey.
Yes.
And he was...
That was the guy's name. And didn't he say with Excel, he was one of the
he was
first...
involved with Microsoft.
Yeah, with Microsoft. He was behind Excel.
First.
And he got this thing going, and his name was attached to it initially.
Yes.
And then ironically, they then also called it the Large Synoptic Survey Telescope, LSST. And notice there's a play on letters here. They now call it the Legacy Survey of Space and Time. So they've kept the initials the same. But I know that now, and I could tell you what proportions go to what institutions, but most of these places are big institutions, universities, and philanthropists as well.
Lots of different groups are a part of it.
Yeah.
It looks like, I've just Googled it.
Yeah, Mitchell's just Googled it. Yeah,
It looks like it's a joint initiative of the US National Science Foundation and the Department of Energy's Office of Science. So, and it's operated by Noir Lab and the National Accelerator Laboratory.
Yeah, there you go.
So it's American. It's American funding.
The American base, yeah. With also with the name Vera Rubin, she was American. She was American astronomer as well. So they got their plug in there. Yeah, just this gentleman here. Just not come back yet.
Oh, hi there. What about light pollution from satellites? Is that going worse? Is that worsening over time?
Yeah, light pollution from satellites. That's always a problem. I would like to think with 15-second exposures, it won't be such a big problem as say when you're looking at something for 2 hours or something like that. 15 seconds is going to be, they'll be able to clear a lot of that noise and rubbish out. But it's always, I think, going to be a problem with astronomy, and there's going to be more and more satellites up.
That's the thing with these alerts they're going to get, of these 10-minute alerts, some of them will be things like satellites or cosmic rays, or that just hit a sensor of things. They will be things they have to filter out, they know to filter out, but the risk is how strong do we filter?
Yeah, interesting.
So the elements there, like you said, in the desert, like the dust and the sand, does it have any havoc on the structure? What year was it built, the structure?
Yeah, the structure's been built probably over the last 10 years or so.
Last 10 years?
Yeah, and it's very recent because it's only just been commissioned. They've only just released in June, and the science has only just started. So this is brand new. So it's just in recent years. In terms of the desert, it's a lot of this sort of, it's quite salty, sort of dry and salty up there. So it's not like a normal desert where there's just dust storms. Because you're such high altitude, you've got minimal wind up there.
You've got rarefied air and it is very salty.
Yeah.
The Atacama was a large salt desert.
Yeah, correct. Yep.
It's just dried out.
Yep. It's just dry salt beds, essentially, the Atacama Desert. Yeah, and as the gentleman says, the air is very rarefied. You're above most of the water vapour. So they go there on purpose, that the air is perfect. Well, when I say perfect, it's the most optimal place on Earth you can get for a telescope. High altitude. Yeah.
Chris,
Yeah.
some of the SpaceX satellites have come out of the sky by now.
So what was
Because you do know how they have about a 5-year lifespan.
Yeah, satellites, yes.
Would have all been fallen out of the sky by now? So they would have put new ones up.
I don't think that satellites falling out of the sky is a problem with...
I know it's not a problem, but
Yeah.
I'm just thinking a lot of them, so there's been a SpaceX that had their satellites up there for a long time now.
Yeah.
A lot of them would have fallen out of the sky by now, right? And like
They're putting up new ones. I see what you... Yeah, they're putting up new ones all the time to replace those, though. Yep.
Yeah.
They are putting them up all the time. Yeah, never.
So they don't do any spectroscopy on this?
Correct, they don't have a spectroscope. Yep, they use the photometric method, which is more suited to surveying. Yep, and leave the spectroscope for a totally dedicated spectroscopic telescope with your high resolution,
And so I thought the type 1 supernova are identified by the spectrum of it.
Yep.
How are they identifying those?
How will they identify those? I wonder whether perhaps communication with other telescopes, notifications and stuff, but also the sudden brightness in the sky, put their filters on, work it out from there. Yeah, because they're not going to be interested so much in analysing it, they just want to know the brightness of it for just purposes of distance for redshifting.
Yeah, that's right.
Yeah, so they're not interested in analysing it any deeper than that.
There's too much data for them to really deal with.
Yeah.
But they're using blockchain now, aren't they?
Yes.
Blockchain's being used for
So, and that's the point I think what Niven's raised there too is you can't do everything, but that's why these days it's sort of multidisciplinary astronomy, that all the different telescopes all combine to make up a picture of the same object, and they all communicate. Hey guys, to a signal to the community, we've just detected a 1A supernova. Oh, another telescope, or we'll have a closer, we've got the best spectroscope, we'll analyse it, what its elements and so on there, and someone else, like these guys say, we'll have a quick look at that for our survey, thank you very much for how far away.
Because that's an early warning system.
In a way, yep.
So, you know how you were talking about filters earlier, and you were saying how it does it every 15 seconds.
Exposure, 15-second exposures.
2 exposures.
Yeah.
And it maps out the sky in 3 days, and then it just keeps going.
Yes, the southern hemisphere, yep.
When do they change the filters to change it into a different spectrum?
Oh, okay, they may do that either the second time round or just within that 15 seconds, they may decide to flick over. I'm uncertain the exact answer to your question, but I'm speculating here, either on the next round, or they might see something really, really interesting, and they might just maybe take another exposure there. They've got the choice of doing that as well. Yep, because they know where that galaxy is. They use the different filters for determining that Lyman drop-off point, so they know exactly that part of the sky, and they just come back to it in 3 days' time, perhaps, and just have another filter ready for it. Most likely, I suspect that'll be it, because they want that 15 seconds of exposure at big distances. So I'm speculating that's the most likely way I would imagine they'll do it. Yeah.
What is blockchain technology? I keep hearing it.
Well, this gentleman here probably explained that better.
Well, I'm not. I really. I'm not a specialist in that area, but it's I don't know much about it, but I do know that it's being used for the large array, the large radio telescope array.
You're using about interferometry.
That's right.
Yeah. So the Jordan was talking about interferometry
Because it can store and process like 1,000 times at the rate of.
And that's like where you get all different telescopes all linked in together.
That's right.
Operating at a size, and it's more particularly radio telescopes.
Yeah.
They'll link actually the Keep 1 and 2 do it. You get an array of telescopes and you link them together, and the effective size of the system that you've got is effectively the size of your telescope. And the Event Horizon telescope uses it. So essentially, you've got telescopes around the world. You've got a radio telescope the size of the Earth. It's called interferometry. And you look at the telescopes here.
Computer systems can't
and
it's being used now.
Yeah, and sophisticated computer systems need to bring all that data together at slightly different times, slightly different locations around the Earth. Radio telescopes use it a lot, and their arrays, those big telescope arrays, they use that. And essentially, you're getting a radio telescope the equivalent size of however big your array is. Yeah. But the Keep 1 and 2 telescope in Hawaii have done that. I know they stopped it for a while because their data was too much, and I don't know if they've restarted it. Yeah.
Not too far away from River in the Atacama Desert is the VLT, the European Very Large Telescopes, and they had 4 8-metre telescopes there that, while they can use them visually, the 4 light from all 4 come back to the one single point exactly the same, and they've got it worked out so all the fibers come back the same length, so the same light appears back at the instrument at the same time. And then what they get, the equivalent is not an 8-metre telescope, they're the equivalent of the distance between the telescopes as equivalent.
That's a resolution issue.
It is, yeah. It's essentially your size, you're increasing the size of your telescope, and the bigger this telescope, better resolution, so you can see brighter objects, and make objects more brighter, the distant faint objects, and bigger images too, bigger and brighter images.
Of these projects now, you think it's hundreds of millions of dollars built these observatories. The biggest part of the budget for most observatories now is the IT to process the data coming off. Computers cost more than a telescope now, just to process the amount of data they're producing.
Yeah, so interesting stuff, isn't it? It's really, fascinating.
Thank you very much. Who actually funds all that? It must have all the data. Who processes it?
That's a whole field in its own right. Processing it all. That's a whole field in its own right, processing all that data. And they're going to need AI definitely for that. But we're going to see more and more of this new technology coming online with other telescopes as well. Now, in 1 month's time, we've got Jonathan Park coming up from Hamilton, and he's going to be talking about the depth of the night sky, where he's going to pick on a few constellations and then go really to ultra deep and look at and use the computers and graphics and look at the constellation you're familiar with, but from different angles, going to different depths and stuff too. So that's fascinating. So so Jonathan's coming up next month for that. Otherwise, I think
just remind too, Chris, because of the Birders Dinner on the 1st November, our guest speaker is also giving them monthly meeting talk on the first Monday, the 3rd of November. So next month's introduction to astronomy will be the second Monday.
Correct.
The 10th of November.
10th of November it is, Jonathan. Yep. So, all good. I think, are we all done?
Yep.
No questions online or anything? No? Thank you very much, everyone. Drive home safely. Thank you. Right, I can stop.